Okay, so why don't we go through and we're going to run this now with 5 groups. So what I'm going to do is click on Analyze, and then we'll go to General Linear Models. I'm sorry, General Linear Model, and then Univariate. And why don't we go down and we'll find our variables. So we want to use total perceived stress as the dependent variable. And then our groups, we're going to use the age group broken into 5 bins. And then not marital status, but sex. There we go. Now, I'm going to do this just a little bit differently. As I was sort of reviewing through your text, there was one analysis that was not included in the examples in Palette, so we're going to skip that one. So we're going to go over here to models and contrast. We're going to skip models. In contrast, there's really nothing that we need to do. In plots, we're going to plot the age group and then sex. Okay, so do that. Oops, I forgot to add it. I always do that. I always forget to add that. There we go. Got to click add. All right, then we hit continue. We're going to run post hoc tests. Okay, and the post hoc will only be for the age group since sex is a dichotomous variable. We don't need to do that. I'm going to select Tukey's, and then why don't we select Bonferroni and LSD as well, just so that you can see the different post hoc tests and the results that they give. Hopefully they'll be exactly the same in their conclusions. Okay. If we go under options, now this is the part that in reviewing Palette, what I noticed is that Palette doesn't actually have you do this part of the analysis. So um, you don't have to pass over age, sex, and then the interaction up here. This will yield some output for planned comparisons, but again, I don't want to confuse you by having you do things in the video that aren't included in your text. So let's just skip that. We'll come down here and click on these 3, descriptive stats, estimates of effect size, and homogeneity tests. Now, Palette does not have you clicked on observed power. I kind of like to do that just because the observed power effectively tells you, given your effect size, your alpha level, the type of test you're running, and so forth, what's the likelihood that you could detect a statistically significant difference. And as your n is smaller, as your effect size is smaller, and so forth, power tends to go down. We don't report that typically within a manuscript, but I kind of like to just look at it when I go through an analysis. So let's hit continue. And that's pretty much it. So now we'll run it. And up comes the output. Okay, so there's our ends for each of the age bins. Here are our descriptive statistics, and none of this is really going to change too much, except that now you see we've broken down the age groups into 5 age groups rather than just 3. Okay, come down to Levine's test of equality of variance, and it's non-significant, which is a good thing for us. It's 0.418. So what that means is that across conditions, what we're seeing, and within the cells, we're seeing that the variability is pretty equal across all of those different combinations. So we don't need to worry that that we violated that assumption. So we can move straight on to the tests of between subjects effects. We come down here to the significance level of the corrected model. It is statistically significant. What that tells us is that somewhere in there we're going to find either a main effect or an interaction effect in the ANOVA. Okay, so we're going to skip the next line that says intercept and then go down to the following 3. These 2 represent our main effects, and here's our interaction effect. And what you can see looking at the p-values is that there's an insignificant interaction effect, but significant main effect. So there's a main effect for age and a main effect for sex. Okay, so now we just got to find out where those are, and that takes us down to our post hoc tests. So we get down to the post hocs, and it presents all 3. Remember, I clicked 3 off because I just wanted to see if we get the same results across every single one, and you'll see some minor differences. So there's Tukey's, there's least squares difference, LSD, and then Bonferroni. Okay, So, as we look across it at Tukey, what we find is that we get an asterisk on this particular combination. So the 18 to 24-year-olds compared to the 25 to 32-year-olds, and then the 18 to 24-year-olds compared to the 50-year-olds. Okay, those are significant. They're less than 0.05. So if we continue to look down at all the possible combinations, I think what we're going to find is that that represents all of the significant differences, right? Yeah, so we look across here, we see it, and we look across here and we see it, but that's really redundant with what we saw right up there. Now let's go down to least square difference, and you'll notice this tends to be the most liberal of the post hoc tests. And one of the things that you'll notice right away is that it's giving you a different pattern of findings. Okay, it's saying that there are significant differences between the youngest age group and the 25 to 32-year-olds, but then also the 33 and 40-year-olds, the 41 and 49-year-olds, and the 50-year-olds. Okay, so it's just think of it as a metal detector that has a higher sensitivity setting. It's just finding things, differences that are more statistically significant than Tukey would. Okay, Bonferroni is a little bit more conservative than LSD, so when you come down here, you'll see that it actually seems to agree the most with Tukey in terms of where the differences are. Right? In fact, it's finding the exact same pattern. I don't know if the p-values are going to be the same or different. There's 0.006 and there's 0.012, 0.06, 0.014. Yeah, at any rate, it seems to me that probably the best way to handle this, that you're getting different post hoc results, the best way to handle it is that Tukey is the primary one. And if Tukey didn't identify, if Tukey didn't identify significant differences in mean comparisons, then we'd start looking at the other ones. But since it did, even though we have this output here, I think we probably are pretty justified in simply ignoring it and then just going with what we have there. Okay. So yeah, sometimes it's a little bit more art than science, frankly. So you just have to go with rules that make sense. Homogeneous subsets. What's interesting about this is that the youngest age group in particular seems to have the highest mean, right? 28.60. It's not all that different from the 41 to 49-year-olds and the 33 to 40-year-olds. But as you get older, um, into the 33 and 49-year-olds, you'll see that these folks pretty much overlap with the youngest group. The 50-year-olds have the least amount of stress. What's interesting, as you kind of look at this, is these 25 to 32-year-olds that are in the group right after the 18 to 24-year-olds, and they seem to be closer to the 50-plussers. So there's some sort of like dip right there, right, in terms of stress, and then it comes back up, and then it goes down. So I have to think about that. Why would that be? At any rate, um, it would be an interesting theoretical question because it's coming up as statistically significant. You can see the 18 to 24-year-olds and 25 to 32-year-olds. Tukey's saying, yeah, they're significantly different from one another, and then the 18 to 24-year-olds and the 50-year-old plus are different from one another as well. Okay, and so you get sort of an interesting pattern there. It could be due to just sampling stuff, even though we got a statistically significant result. Remember, you can get significant results that don't, in fact, reflect the population. But if it's a significant result, of course, the odds that you're making an error go down and down. Um, in fact, if you look at Tukey's, what it's telling you is that the odds or the probability that you would observe a mean difference of this size given the n that we have is, what is that? Getting pretty close to 6 in 6 in 1,000. So it's unlikely, right? And the difference with the 50-year-olds is about what, 1 in 100. So yeah, we'd have to sort of think about why that would be, and replication, of course, would be the strongest bit of evidence for that. So that's pretty much the printout, and how to interpret it. By removing that one option, it simplified our printout quite a bit. Um, and I think what I'd like you to do now is run one more test that uses a different dependent variable, and let's see what results you get.